Well, welcome, Michael. It's been fabulous having you here in the Seattle region. I should say we had you last night at Town Hall with Aaron Roth, your co-author of the new book, The Ethical Algorithm, and just now we had you at the Microsoft Research Distinguished AI Lecture, and a lot of fun and great engagement with the audience. I wanted to start by saying that I've always admired the constellation of topics that you've explored, your set of interests. I'm curious how you got to where you are, going back a little bit into your maybe high school, undergraduate days, and what's your path like, and how would you describe how you got where you are?
I guess in many ways my path was a little bit untraditional compared to kind of our peers. In high school, I was a pretty diffident math student. I didn't find it very interesting. I would often slack off. I would make up for a run of bad quiz scores by, kind of suddenly panicking and kind of evening things out. And in high school, I was the topic I was really most excited about was kind of English and writing and journalism. So I did a lot of kind of local journalism for the San Diego newspaper in the neighborhood I lived, this sort of thing. And so when I started becoming more interested in math and science towards the end of high school, but started college as an English major.
That's very interesting.
And, I think pretty quickly realized that I decided to major in English because I wanted to write. And I came to think that it was going to teach me how to read more than it was going to teach me how to write. And at that same time, my math and computer science classes started to become much more interesting. I was, beginning to...
Where did you go to school as an undergraduate?
Berkeley. And that was kind of in the first wave of computer science being kind of a popular major. It was kind of increasing in awareness, not the frenzy that we have today. But certainly once I sort of saw the more creative side of math, like proving things, or the creative side of computer science, like building stuff, then at some point I think I never looked back.
And so you went up to grad school. Where'd you go to grad school?
I went to grad school at Harvard, and I went straight from undergrad. And that was a bit of a culture shock because I'm a native Californian and I'd never lived on the East Coast before, so I had to adapt to that. And I also, at the time, Harvard was a much smaller department than it is now.
Applied mathematics department.
No, it was actually computer science by that time. Yeah, it was by that time. And I really went primarily, in the hopes of working with one particular advisor, which was less valiant. But I do remember feeling, the first year of grad school kind of narrowed and claustrophobic because I'd gone from this, huge state school where I did, continue to take classes in the humanities throughout my entire time, to suddenly, taking only computer science classes and only being around computer science people for most of each day. And so that was sort of an adjustment that I had to make that probably every doctoral student has to make early on in their career.
Did you know Les's work? Did you know you wanted to do computational learning theory at that time?
I did, and that's more or less what I went there to work on. So I think, by late college, I knew that I was attracted to the more theoretical, algorithmic, mathematical side of computer science at that time. But I also knew that I wasn't especially interested in a lot of the traditional optimization style problems that were kind of the bread and butter of theoretical computer science at that time. Either complexity theory, which I found very interesting, but is a hard field. But even the algorithmic side at that time, we weren't at that kind of computational lens phase anymore. Computer science and theoretical computer science in particular still studied optimization problems like traveling salesmen and graph coloring and all great classical stuff. But I knew that somehow I wasn't as interested in that as in taking that same way of thinking and applying it to less traditional topics. And so when I learned about Valiant's work in learning, which was quite new at that time, I think his first paper came out in maybe, I graduated Berkeley in '85, and I think the first paper was maybe '82 or '83. It was a revelation to me, and I sort of thought, wow, yes, you could take these same ways of thinking, these same algorithmic tools, and think about like a natural phenomenon like learning. And that I found very appealing and sort of decided to roll the dice and maybe go to a smaller department than I might have in order to hope to work with him, and that worked out well in the end.
Now, how did you go from your focus on computational learning theory into the game theoretic world and into the algorithmic game theory? How did that
Yeah,
flow
it's
like
funny.
there?
I'll admit that maybe I'm just like not sufficiently reflective, but I'd like to claim that there was sort of some grand plan in my mind and connections between these topics, and really I wish I could, because there was this period where I just became interested in game theory. There wasn't really such a thing as algorithmic game theory at the time. There weren't any known connections at that time between learning theory and game theory, or machine learning and game theory. And so this was just some other interest that I had, that I thought like, somehow at some aesthetic level these things seem the same to me, like the sort of level of sophistication of the mathematical arguments, the sort of focus on models that have strong foundations but that might be applicable to real world situations. And so I don't know, for like a decade I just kind of carried these interests separately, and then at some point it didn't seem so weird anymore to have these two interests, and then there were other people working on them as well. I'd like to say that like, I planned for that convergence to happen or saw it coming. It was really just two different interests. And I think more generally, one of the reasons even though I've worked on a lot of different topics, some of which are not considered primarily in the purview of computer science per se, I always think of myself as a computer scientist first and foremost, in the sense of kind of in the imperialist sense of computer science. So my view of computer science is that one of the greatest things about the field is that collectively computer scientists don't really seem to pay much attention to disciplinary boundaries, right? So the AI community in particular is, rife.
Guilty as charged.
So it's like, rife with examples of where we waded into some topic and started, doing research and writing papers in it, and then, we discover like, what you call reinforcement learning is called like, learning and control theory, and it's been around since like the 40s. And so we have this habit as computer scientists, I think, of, if something's interesting, wading into it, embarrassing ourselves for some amount of time. But in the specific case of reinforcement learning, even though there was some rediscovery of the wheel, eventually computer scientists made like truly novel contributions
Absolutely.
that needed to be made from people with an algorithmic computational perspective.
Now in some of your game theoretic work, you very interesting in a direction you dove into behavioral studies with human beings. You want to tell us more about where that came from and some of the studies you did?
Yeah. So at Penn I teach, and I have now for many years, a large undergraduate survey class called Network Life, which is, this is kind of I wouldn't have described it this way when I first developed it, because these terms didn't exist. But it's kind of a survey class on network science, on sort of the science of social networks, and how influence or content spread in a social network, and also quite a bit on computational social sciences, we would call it more broadly. And so I have fun with this class. It's sort of a class I designed to also dovetail with my current research interests, rather than kind of teaching a textbook subject out of the classic textbook. But to make things real, I sort of started doing these in-class experiments in kind of collective behavior and strategic interaction in networks and things like this.
Some examples of things you did.
So I think like one of the things I do in the first day of class is I say, like, just to sort of illustrate these kind of 6 degrees of separation ideas, is I say, okay, everybody look around the room and basically consider yourself to be in a network, and your neighbors in the network are anybody that you see in this room that like you've met them before in person, okay? And so everybody looks around, and then I toss a tennis ball to somebody. And I say, okay, your goal is to get the tennis ball to that person in the back left of the auditorium, but everybody can only like throw the tennis ball to somebody that they know in the class, okay? And sometimes I ask the person at the back of the room to give a little information about themselves, like their hometown and their major. But basically, people try to toss the tennis ball around, and we see how many hops it takes for the tennis ball to get there, and it always gets there. And then we say, like, okay, that took 4 hops. Is that good or bad? How could we know? And then I say, like, well, one way we could know is by kind of doing a crowdsourced breadth first search. So what I do is I say, like, okay, the first person I give the tennis ball, you stand up. Okay, now anybody who knows this person, stand up. Okay, and then I say, now anybody who knows anybody who's standing, stand up. And we just keep doing this in synchronized waves, and we see how many waves of standing it takes to get the person in the back of the auditorium, and that's the shortest path distance, right? So this is the kind of thing I was doing. Okay?
I have to say that when Yuri Leskivic and I looked at messenger connections by this acquaintance graph, we were just stunned to see 6.6 degrees for messenger spanning the planet.
In many years, I've assigned that paper in this particular class, by the way, along with sort of the Facebook 4 degrees of separation paper that was a little bit later. But so, I was kind of doing these in-class demos that were fun and interesting. And I thought, I could try to do this in a more controlled laboratory setting. And so actually with Sid Suri, who's here at Microsoft Research Redmond and is a close friend and colleague, he was a grad student at that time and had this, I think, a similar kind of, devil may care attitude about research, like, it's wacky, we know nothing about this, what the hell, let's try it. And so we designed laboratory experiments in human subject graph coloring. So what we did is we brought like a bunch of students from the class into a workstation, a lab full of workstations, I think like a little less than 40 workstations, and we built and designed software that basically gave a GUI where you had you were a vertex represented in the middle of the screen. You saw your neighbors in that network and the edges between your neighbors, your so-called like local or ego network. And there was like an action bar at the bottom where you had to choose what color to pick to be your vertex, and you'd be able to see the color of your vertices, your neighbors in real time. And so, I was trying to see in small, on small networks of our design that the students didn't know about. First of all, could people do this stuff at all, right? Could they, in a short amount of time, actually coordinate to find a proper solution to the graph coloring problem in a few minutes or so? And secondarily, if they are able to do that, how does network structure matter? Are there certain types of network structure that are behaviorally more favorable to finding a solution quickly and others that are more difficult? And what can we say about why that might be? And so we did this, and it was kind of wacky, and we had no idea where to send this kind of work. And I was already quite friendly at that time with Duncan Watts, who was at MSR New York for many years, but has now joined us on the Penn faculty. And he'd done human subject work and was a leader in network science already at the time. And he's like, oh, in his great Australian accents, you should send that to science. And I'm like, okay, and he, and so it took his advice, and he gave us some good like expository advice and it got in. And so at that point, I think we kind of had to decide, like, okay, was this sort of a one-off, kind of almost like a scientific joke, or are we serious about these kinds of questions? And I decided I was serious about them, and so this led to a long string of behavioral work over like a 10-year period in which we, played around with different tasks, including ones that are related to kind of influence in voting decisions, and a bunch of other problems, and also, explored the network structures. And it was fascinating work. I learned a lot from it. Still feels a little bit wacky to me, but I'm glad I did it.
No, but I think it helps to define a whole paradigm of effort, and hopefully it's inspired many other studies like this.
Yeah, speaking honestly about that work, I enjoyed it greatly, and often find myself thinking about behavioral human subject work, and we've been doing a little bit of it in sort of fairness areas more recently. One of the reasons I kind of deliberately stopped that line of work was that, first of all, that line of work gave me tremendous respect for people that do careful human subject work. And I learned a lot from many such people, although all of the errors are mine, as the cliche goes. But one of the things I realized at some point is just like the design space that we were considering, where your design space includes all of the possible networks that you could impose on the experiment and all of the possible distributed behavioral tasks that you could ask subjects. Early on we had to decide, like, okay, we have these interesting results on coloring. Do we now go deep on coloring and do ever more refined experiments on coloring? Or do we kind of do more of a shotgun approach? And I kind of felt like, well, this is such an unpopulated landscape that really it would be more fun and serve science better to take the shotgun approach for a while. But then after 10 years of doing it, I was just kind of like, this is never ending, right? I could do nothing but these kinds of experiments with the rest of my career, and there would be no clear stopping point. And on the other hand, when I thought about the deep dive into one particular task and, let's say, type of network structure, I was reminded by the extensive literature, let's say, in behavioral game theory on, repeated prisoner's dilemma or the ultimatum game, where the same experiment has been run hundreds or thousands of times with slightly different variations in different cultures, et cetera, and I was just like, that's not for me either. And so I kind of, at least temporarily retired from that particular line of work.
It's great to have you with us for the Microsoft AI Distinguished Lecture, but coincidentally, you're also on a book tour, and I just finished your fabulous book, The Ethical Algorithm. And first, let me ask you, what possessed you to write a book with your colleague, Aaron Roth?
Yeah, I mean, I think it was the combination of the rising societal awareness of the negative consequences of large-scale algorithmic decision-making, including that kind of perpetuated by machine learning and the standard machine learning pipeline. Things like models, predictive models that are discriminatory by race or by gender, or that leak private information from the training set, these sorts of things. So we kind of watched with everybody else the increased media reports about these things and the popular books that were written on these topics. On the one hand,
many quite negative, right?
Yeah, most of them, I think, kind of just correctly highlighting the problem and telling people this is being done with your data, and these are the bad things that can happen to people, including yourself, from the use of that data. So we kind of, like everybody else, saw that this could happen. And on the other hand, Aaron and I are, both for the last 5 years or so, have been primarily working on how you would design algorithms to avoid or at least reduce these kinds of harms in the first place.
So as opposed to having well-defined algorithms that are simple, for example, and understandable in their goals, like minimize cost
Right.
In their use, or average cost, thinking about actually enhancing them, extending them algorithmically to address some of the concerns, rather than bringing in lawyers and necessarily, or sort of regulatory activity to control them.
That's right. I mean, we also believe that regulatory and legal approaches and improvements are needed as well. But, first of all, those are slow. And also, by definition, they're sort of after the fact, right? So when the FTC fines Facebook for some, privacy violation, it's happened already, and here is the punishment for that thing, okay? So these kinds of approaches are both slow, and they tend to be after the fact. Now, sometimes, things need to be slow and they need to be after the fact, but as scientists, we also know demonstrable ways that we could make our algorithms better from a social perspective. So instead of just minimizing the error, I could, minimize the error under the constraint that, the rate at which I'm falsely rejecting women for loans is not radically higher than the rate at which I'm rejecting men's for loan, right? We know scientifically how to write that problem down, and we know algorithms for solving that problem. And so, getting back to the impetus for writing the book, we really felt like there was a need for a book that kind of followed in the steps of books that came before us that pointed out what the problems were and largely suggested the kind of regulatory and legal solutions that you suggested. We felt there was room for a book that said, hey, while you're waiting for that, here are things that, we and companies and individuals, scientists and engineers could change about our algorithms right now and, maybe not fix all of these problems, but at least improve them and put like the discussion of them on a scientific basis rather than kind of an ad hoc basis. And so that's why we wrote the book.
Now, what's your sense for the limits of how far we might go? Let's still go with fairness right now. On the algorithmic front, where we have so many possible choices and interpretations, it seems that there is going to be some notion of in whose eyes do we behold the fairness. And I wrestle myself at times looking at these very crisp definitions, and it's fabulous to see these approaches incrementing on the prior, more naive approaches per goal, and addressing some of the concerns, for example, with obvious unfair or biased inferences. But where do we see choices and process going when it comes to figuring out which one to apply in reality?
Yeah, so
which particular configuration.
Yeah, so we've discussed this at some length in the book, and in particular, as you know, most of the definitions of fairness that have been proposed in the algorithmic literature require one to first sort of specify who you're worried about being harmed by a decision-making process, algorithm or human, right? And then what would constitute harm to that group. And then you're in business to sort of say like, okay, let's say you're using machine learning, learn a model that tries to minimize the error but makes sure that it obeys this fairness constraint that we've written down. And as you've alluded to, the one qualitative problem with this area is that there's lots of different groups I could protect and lots of different mathematical definitions of fairness that I could specify.
Right.
And we already know, unfortunately, that some of these combinations are incompatible with each other. So it literally might be that you have a data set that faces you with the problem that if I ask for more racial fairness of some particular variety, the only way I can get it is at the expense of increased gender unfairness, okay? And so in all of these different, implementation of social norms and algorithms, there's always going to be this trade-off between the social norm and accuracy. In fairness, it's even worse. It's like even ignoring accuracy, asking for more of one type of fairness that you want might mean that you have to have less of another.
So I guess my reflection has been, as we get more transparent and clear thinking about the different definitions and how to precisely execute the goals in our algorithms, there's a framing of a really hard discussion that needs to happen somewhere when it comes to the applications that we as a society, I think, have not figured out how to actually execute on.
That's exactly right, I think. And the way I might put that is that, especially in the instance of algorithmic fairness, I think one of the main virtues of the science is that it can identify what the really hard problems are, what the problems are that really need to be worked out by human organizations and society. And you might think like, okay, well, so what's science good for if what it does is identify, the hard problems that science can't solve? I mean, I think this is exactly one of the values of science in general, right? Which is that if you look sort of before the flurry of work on differential privacy and on algorithmic fairness, there was confusion about what part of this was hard and what can be solved scientifically and algorithmically, and what are the parts that like really algorithms can't do that for you no matter how hard you work on them. Somebody has to make the decision about whether we're going to trade off racial fairness and gender fairness and by how much and at what cost to accuracy. So just to be clear, I know it's clear to you, but just for the viewers, right? Our book and the research fields that we are representing in no way suggests that algorithms should themselves decide what fairness or privacy means. That we view as something that remains firmly in the social and human domain. But, until all this flurry of work on fate topics, I think, we really didn't have a clear idea of what the boundary was between science and society. And I think, in my view, we're discovering that science can do quite a lot algorithmically, but it can also just show us what it can't do in a way that we didn't know before. And so our thinking on these topics was just fuzzy before, and now it's becoming crisper.
Kind of interesting to apply the clarifying lens to figure out where we now know it's a social, societal, people-oriented set of questions that need to be decided.
Right.
And to ask by whom.
Yes.
And before, it wasn't so clear as to what was going on, and so the algorithmic perspective really helps us with that border.
Yeah, and I find that, I think one of our goals for the book is, of course, we would love it if this became, next summer's Hamptons beach read. But I think more realistically, we're hoping that this book can kind of lay out the landscape that we're talking about for kind of a core audience that includes people like regulators, policymakers, social workers, legal organizations, and the like. Because I think, again, one of the motivations in writing the book was as I started talking to people from those parts of the world more in just the course of the research that we're doing, I realized these are very smart people, but to them sort of the entire algorithm, machine learning, AI pipeline, the whole thing is this black box. And I felt like I was getting comments of the kind that well, this is just so complicated, nobody can understand any piece of it whatsoever. And that's not true. We understand many parts of this pipeline extremely well, and many parts of this pipeline have very, very well-founded scientific principles that trained smart people are applying. And in some cases, it might be those very principles which are the problem, right? So it's just sort of, if you optimize just for accuracy, you shouldn't expect for free to get fairness of some kind, right?
You can almost see a follow-on book that starts with the foundations laid out on the principles that you write so eloquently about. And it's all about, let's just take a few data sets and a few trade-offs and reason through how you think about the social aspects of these decisions.
Yeah, kind of a deeper dive, if you like.
But on the social societal side, on the process side, looking at how we might even begin as a society, even considering the governmental agency mechanisms we have in place right now, and social, societal, civil society feedback mechanisms. How do you actually do it?
Yeah, that's a great suggestion. My first reaction to it is that
Michael, don't be pessimistic right now.
No, I can think of a lot of people that I would like to write such a book. I think maybe a little bit more to the point. I think if people like Aaron and I were to write that book, we would want collaborators on these case studies because, in particular, these decisions about, whether it's worth trading off this type of fairness for that type of fairness, or, this type of fairness for this much less accuracy. These need to be very domain-dependent, decisions. The stakes matter. It matters whether you're, making decisions that influence people's parole decisions versus what ads to show them. And so you want to have people that really, in whatever particular domain that you choose, you want people that have thought about all the different angles.
I have to say that speaking of the real world, it's even messier. The reality is even much messier, as we all know, than even the clarified worlds that we come up with, separating out the social from the algorithmic. On the Partnership on AI board, we had a meeting in Philadelphia, your hometown recently, where we sat with a number of officials from the criminal justice system in Philadelphia, which has particularly traditionally has had high incarceration rates. And in the context of risk scores used for recidivism, heard about the reality of how things really work with bail and incarceration and arrests. And it seemed so complicated and messy that even the clarified views we have when we think about these challenges in our abstractive versions of these problems are way different. So.
Yeah, and I've been exposed a little in a different metropolitan area. I'm on a sort of an oversight or advisory panel for a city that's basically trying to revise its risk assessment models and is particularly concerned with fairness. And again, it has not made me an expert by any stretch of the imagination, but you just realize that if you think about building a model to predict failure to appear. So somebody's been arrested, they have a court date, you have to decide whether to keep them incarcerated until that appearance date or release them on bail and how much or under what restrictions and things like this. And then, you kind of get it all into all this stuff that's just not in the data at all.
Yeah.
Sort of actually if somebody is working 2 jobs, then, appearing in court at a specific time might really actually cause them to lose that job, right? They might just be in a job where there's zero tolerance for, and so you suddenly realize, okay, yes, there is this data set, and you want to use this data set to build an accurate predictive model, even under the with the constraint of fairness. So you're trying to do the right thing. But then you learn, okay, actually things are really complicated, and people might fail to appear
for crazy
for sort of
reasons outside
that
the
are
model.
kind of completely legitimate and that you're quite sympathetic to, that leave no trace in the data whatsoever, and therefore aren't kind of represented or spoken for in your algorithm. And so, it's hard, right?
Yeah.
It's sobering.
I love the section of your book where you take the algorithmic lens and put it on the endeavor of science itself. It's a fabulous chapter. I'd like to discuss that more with you.
I think to a first approximation, the reproducibility crisis, which has plagued certain parts of the social and psychological sciences and also the food science area.
I'm worried that it goes further than that, by the way.
No, I am too. But these are the ones I think that have been the most publicized,
Yes.
right? So, by the way, in writing this book, we debated whether to name names of people that had been kind of caught up in this kind of scientific scandal, and ended up doing so, but also feeling a bit bad for them.
But scandal implies that it was done with knowledge.
In some cases, it seems like it was. In some cases, it wasn't. But just to be clear, for the viewers, the types of problem we're discussing here, I think at some high level are versions of overfitting, or more precisely of kind of communal overfitting. And so the problem is, I gather some data set, and I'm interested in okay, is it the case that, I don't know, drinking more red wine improves your lifespan, for instance, right? And so I gather a large sample of people, and I know about their red wine drinking habits, and I know how long they lived, and maybe I have a hypothesis that that it makes you live longer. And so I look at that data set, and that's not really supported. I can't, the p-value is too big. Oh, but I noticed some other interesting thing in the data while I'm looking at this hypothesis, and so I say let me on the same data set, let me test that hypothesis, and that doesn't quite work out. And then I do this, right? And one technical point that we try to convey in the book is that it's not when you're doing this adaptive data analysis, and your next hypothesis or experiment is on the same data set by conditioned on everything you've tried so far. You don't just have to correct for the number of things that you've tried so far. You have to correct for all of the things that you might have tried under all of the possible outcomes of the thing you've tried. And just to make this concrete, we start the chapter off with a non-scientific example. We say suppose you get an email one day that says oh, hey, I've got a stock tip for you. This particular stock is going to go up tomorrow. Okay. And you ignore it, but you check and the stock goes up. And then you get another email the next day that says it's going to go up again, and it goes up again. And then the third day it says it's going to go down, and it goes down. And sort of after 10 tries in a row, you think like, okay, this person either knows this company very well or has inside information or is a financial genius. And so you agree to pay them some upfront fee for further stock tips that then are no better than random guessing. And of course, the scam that went on, right, is this person on the first day sent 1 million emails, and to half of the people they said it's going to go up and half it's going to go down. On the half that they were wrong, they just give up and don't send them another email again. And on the half they were right, they then branch again. And they're building like a complete binary tree of depth 10, let's say.
So somebody thinks they're really smart.
Yeah, and so you happen to be on that one, you didn't see all the other emails.
Yeah.
As far as you're concerned, your only experience is this 10 correct predictions in a row. And it's not enough, of course, to sort of correct that, like, for 10 things that were done. You need to correct for the 2 to the 10th things that you didn't see. Okay, so this is kind of the problem. And one might seriously worry that we are engaged collectively in this kind of exercise in the machine learning community. Why? Because now there's not just one email scammer, but there's hundreds and thousands of us running experiments on shared data sets. And we're also reading each other's papers. So I see, your improved error rates on some benchmark data set with some particular algorithmic or modeling innovation, and I say like, oh, that's a good idea. I like Eric's idea. We're gonna explore a refinement or variation of it, and we try like 10 things, which seems like a modest number, and then the 11th thing improves on your error rate, and that gets published. And of course, if we tried submitting to the top conferences or journals one of the 10 things that we tried to improve on your method and it didn't work, and our abstract is like, oh, we take Horvitz's recent method and we try this variation and achieve worse error rates, it will not be getting published, right? So the publishing mechanism is kind of like the filtering in the email scam. You're not unaware of how many things were tried and that weren't successful. You only hear about the winners, okay? So this is a recipe for our communally overfitting.
It's such an important problem of our time.
And and it's really, this could have happened in any era, but especially in the era of data-driven science, and I think machine learning is kind of the epitome of data-driven science. And it's also not just that. It's like it's not even just the journals being selective for positive results and therefore kind of perpetuating a bias. Like we're kind of doing it to ourselves in the form of these competitions, right? Where we say, okay, everybody, here's the training set, but we want you to have some sense of progress, so you can upload a model like once a week, and we'll just tell you what your error on the test set is also, right? So it allows us to kind of all exfiltrate. And if we don't know how many of us are trying this, and the exfiltration is sort of too precise in telling us exact error rates, then we're essentially, without any one of us misbehaving or realizing it, we are collectively performing some kind of gradient descent on the test data, not on the training data. And so we talk about this and kind of view it from kind of a game theoretic viewpoint, and then we discuss different types of solutions that are proposed. There's the whole pre-registration movement, which is one solution, but it's a very onerous solution. At a high level, it requires, before you gather any data, you need to commit to what your hypothesis is. You then go gather the data, and you register this on like a official website. You then go gather the data. You are allowed to test that one thing and report the outcome. And then you need to burn that data set forever, right? Not only can you not use it, nobody else can use it either. Okay, so our view is that yes, this is some solution that if really enacted at scale would greatly set back legitimate scientific research, at the benefit of kind of eradicating this kind of p-hacking, as it's called.
Another trade-off.
And it's early days, but it does seem like there are other methods that are more algorithmic that I think are much more appealing. And we discuss those, and interestingly, many of those are related technically to differential privacy.
You've been very successful, Michael, in your life, and when I say success, I mean in all senses of the word, particularly your happiness and joy with what you do. I know also with your family life, from some of what I know about you personally. what are some ideas or insights or recommendations to young people about career?
Yeah, it's a good question. So, again, as per questions and you asked earlier in remarks, I've never been one of these people that's had a 10-year plan in my mind. And when people, I've met people before, not necessarily scientists, but I've just met people that say like, well, I've got, my wife Kim and I at one point met, I think it was like a realtor that was showing us places. And, this guy said like, young guy says, I've got like a 1-year plan, a 5-year plan, and a 10-year plan. I'm like, wow. I can't.
His 10-year plans to get out of real estate.
Yeah, maybe, yeah. And, when I look back at my career, first of all, my overwhelming sentiment is one of gratitude. I feel very lucky to be where I am and feel that, kind of society came my way. And, and I think I might have written one of the first, if not the first, dissertation with the word machine learning in the title. It was certainly one of the earliest. And at that time, as you know, machine learning was kind of this neglected corner of AI, right? And there's very little activity in it, and everything was wide open. And the field has been tremendously successful, and I'd like to think that I contributed something to that. But if I'm honest with myself, I think like, well, really, the rise of the consumer internet kind of moved machine learning and AI from being an important, valuable scientific tool with fascinating research going on into it, into something that was like right in the middle of society. Okay,
middle of everything.
And I'm not responsible for that, even though I've greatly benefited in my career from that trend. So a lot of it was sort of being in the right place at the right time. I think the strongest piece of advice I have for certainly for young researchers is to just relentlessly follow your interests and to ignore disciplinary boundaries, and don't think of yourself as don't think of yourself as anything. Don't think of yourself, I was trained as a theoretical computer scientist. I consider myself a card-carrying member of that community. It forever shapes my view of not just algorithmic problems, but the world more generally. But I don't require, sort of only doing theory work. And, when I became interested in game theory, I just wanted to study it and learn more about it and do research in it, some of which is better than others, right? And so I think, to me, I can't imagine a more burdensome life than doing research, trying to do research in a topic that you're not interested in, right? Sort of like in some ways, the world of research encompasses like the extremes of professional despair and euphoria. Because if you're doing something that you're really interested in, you really love, then it really is like, it's that, oh my God, I can't believe I'm paid to do this. Whereas, even if you're paid to do it and you're trying to be creative and original in a topic that you're not interested in, I cannot imagine a harder thing. So, in my own career, I've just, when I was interested in something, I studied it, I did research in it until I felt like I was less interested in it or didn't have as much to contribute, and then I just, moved on. And I think that's, if you can execute on that, that's just like the only kind of generalizable principle I think I can take. I can talk about specific pieces of work and why I did them at the time. But in terms of generalizable advice, it would be that just keep moving, keep working on what's interesting to you. Don't worry about what's interesting to you now, how it connects to what you did before and how you're going to explain why this makes sense. It's okay if it doesn't make sense even in your head for long periods of time or ever. There's still pieces of work I do where I think like, okay, that was interesting. I have no idea how that fits in with my overall research agenda. It doesn't. But my whole research agenda was created that way, just by following my nose to what I was curious about and interested in.
Yeah, I could explain it as all the things that Michael Kearns has been interested in. It's been great having you, Michael.
Thank you, Eric. I appreciate it.